Okay, yeah, please. Whenever you're ready, Marco.
Okay. Okay. Hi, everyone. So last time we I gave this introduction. A generalized complex structure is. Uh, so actually, I didn't get very far, but I covered a bunch of fundamentals. So the claim, which I never explained, was that generalized complex geometry interpolates between complex and symplectic, and it's inspired by foliations, and it's also contained within Dirac structures. So I'm going to give all the examples today in preparation for the third talk, which will be about generalized scalar. So what we did cover was the fact that these are geometric structures on this kind of this bizarre bundle, which is an extended version of the tangent bundle. It's an extension of the tangent bundle by the cotangent bundle, and for all intents and purposes, we can just treat it as being the sum of T and T star. T and T star are they're dual to each other, and so we get this split signature natural inner product for which T and T star are null. We also have an orthogonal group. We have a Lie algebra, which involves two forms, bivectors, and endomorphisms. So the interesting thing is how these three components kind of extend the symmetries of the manifold, which we normally think of as being described only by endomorphisms of the tangent bundle. Now we have this new degree of freedom in the symmetries. The B field transform in particular is this kind of shear which moves in the cotangent direction. We talked about the integrability condition for, so the definition of a generalized complex is that it's a complex structure on this extended bundle. It has a plus I eigenbundle, and that plus I eigenbundle must be closed under the bracket. This bracket is given by this expression. It's a natural extension of the Lie bracket. Satisfies the Jacobi identity, and the interesting thing is that while this bracket is not a Lie bracket, if you restrict it to a subbundle which is involutive, which is closed under the bracket, and which is also null in the inner product, then this bracket does become a Lie bracket. And so we get we basically get a source of Lie brackets in this way. Okay, so let me give another definition to start it off today, and that's the definition of a Dirac structure. Dirac structure is a subbundle. So this is a generalized foliation. So instead of having a subbundle of the tangent bundle, which is closed under the bracket, under the Lie bracket, we're going to have a subbundle of the T plus T star, which is maximal isotropic. So this condition is maybe not so essential. We could consider subbundles which are not the maximum dimension, but anyway, that's the definition, such that the subbundle is closed under the bracket. So by which I mean sections. If you take the bracket of two sections, it's a section of L. So an example of this is the plus I eigenbundle of a generalized complex structure. But let me give some more fundamental examples of it. So I'm going to give a bunch of examples. So number one, or maybe zero, is that if we look at T inside T plus T star, then it is closed under the bracket. And the bracket is, because of the fact that it's just an extension of the Lie bracket, that implies that it is closed under the bracket. It's a section of T. Now, I want to remark at this point that that the Courant bracket is not just a single entity, but it has a parameter in it which typically we set to 0. But so let me just remind you. So if I have a vector and a 1 form and another vector plus 1 form, then this will be the Lie bracket of x and y, the Lie derivative of eta minus iy dxc. Okay, so this is the vector part of the bracket, and this is the covector part of the bracket. And so, yeah, so for reasons that, well, for various reasons that I could use to motivate this, but let me not go into it. You can deform this bracket by adding a term of the following form. You take the double interior product of a 3 form. So sometimes this is called the twist, but whatever, it's just a parameter in the bracket. We could put that 3 form as a parameter in the notation. And the point is that if dh is equal to 0, so if this 3 form is closed, then the same axioms are satisfied by this bracket as would have been satisfied by the original bracket. Okay, and what I want to emphasize here is that any such 3 form is locally exact by the Poincaré lemma, and this bracket it actually satisfies maybe the most important lemma about the Courant bracket is the following one: that if we take x plus c and we deform it by one of these B field transforms, then by definition, what does this mean? Remember, this means that it's the identity plus the shear into the T star direction. And if we work this out, this will be the original bracket plus some extra terms. Now, the extra term is going to be Lx Iyb minus Iy dixb. And this is Lx Iy minus Iy Lx plus Iy Ix d applied to B, using the second formula that most differential geometry PhD theses are based on. So the first one is this one, dix is Lx. So that's the one we used last week. And the second one is Lx Iy is Ixy. So based on this one, I can convert this one into Ixy b. So that's and then there's an extra term Iy Ix db. So what you see is that this is the B field transform of x plus c, y plus eta. So this term here is the sum of these two terms. but I have this additional term, which is the double interior product on a 3-form, dB. So what you see here, this is the important lemma which explains why B field transforms are more important than beta field transforms, because such a lemma does not exist for beta field transforms or any other symmetries. So what do we see? We see that exponential of a 2-form, which does this shear in the T star direction, is almost the symmetry of the bracket. In other words, if I apply it to the arguments of the bracket, it just comes out in front of the bracket. Okay, so this e to the b is a symmetry of the bracket exactly when this error term is not present, and that is not present exactly when the 2-form is closed. So we can conclude two things from this. Conclusion 1 is that b, e to the b, is a courant automorphism if and only if db equals 0. And the other thing that we can conclude is that if b is not closed, then this equation is not true. This is not a symmetry in general, but we get an extra term which has to do with the derivative of b. That derivative of b enters into the bracket exactly as the 3-form twist does. Actually, maybe I with these signs, well, maybe I might prefer to put them in the opposite order, IY, IXH in the twisting term. And then this will come in as dB. So, so B is a symmetry of the bracket when it is closed, and when it is not closed, it transforms you from a bracket to a twisted bracket, or it transforms you from a twisted bracket to a different twisted bracket, where the twisting 3-form has been modified by an exact term. Okay, so so if your 3-form is exact, you can use a B field gauge transformation to get rid of it, meaning that we can put B, we can tune B so that its derivative kills H and bring us back to the 0 bracket, right? So as long as the cohomology class of the 3-form is equal to 0, we can always do a gauge transformation by a non-closed 2-form to get rid of that twisting. Okay, this is a very special. This is really the key aspect of the. It's really a key aspect of this generalized geometry, because if you want to think about it this way, you could think that in generalized geometry we're enlarging the playground, we're working on a larger space, but the symmetry group is not just the diffeomorphism group; it's also enlarged, and so in a sense, in some sense, the degrees of freedom are the same as they were in traditional geometry, because of this increased symmetry. But anyway, so I just wanted to point out that, so let's do another example which will kind of illustrate this. So in example 1 is that if the bracket is twisted by a 3-form, a closed 3-form, then T inside T plus T star is not a Dirac structure. Okay, because when you take X, Y, if you take vector fields, then what you will get is the Lie bracket of X and Y, but you also get IX, IY, H. and this is in T star, and therefore the tangent bundle is not closed under the Courant bracket. So the tangent bundle is only an example of a Dirac structure if the 3 form is 0. So this only works if the 3 form is 0. Another example, which is really these first 3 examples are all the same example. If we take the graph of B inside T plus T star, i.e. this graph of B, this is really, what I mean is that it's X plus C plus the shear by B for all X plus C inside Tm. Oh no, I'm sorry. I'm sorry. The graph of B is the set of X plus IXB for all X in T. So here what I'm doing is I'm looking at T plus T star. I'm viewing the 2 form B as a map from T to T star, and I'm taking its graph. This is gamma B, the graph of B. And so, how do we determine whether or not this thing is closed under the bracket? Well, this graph of B, what is it really? It's really the B field transform applied to T. And we already discussed under what conditions T is a Dirac structure. So if I want it to be the case that e to the bt is contained inside e to the bt, right? Just notice that this is e to the b with respect to the dB twist. And so if dB is equal to 0, this goes away. This is just the Lie bracket. And we know that T is closed into the Lie bracket. And therefore, we get this condition, under the condition that dB is equal to 0. So in other words, gamma B is a Dirac structure with respect to h equals 0. So the untwisted Courant bracket, it is involutive for any closed 2 form. Okay, so we have for h equals 0, the examples that we have so far are the tangent bundle and the graph of any closed 2 form. All of these are Dirac structures. So they are involutive things. Okay, and so you might say, well, okay, in what sense are these Dirac structures analogous to foliations? Well, a foliation is something in the actual manifold. It's actual directions in the tangent space. So to see whether this gives a foliation, what you could do is take this subbundle and project it down to the tangent bundle. So we can project to T. And what we see in for these examples is that because they are actually graphs like this, that means that the projection onto the tangent bundle is an isomorphism. And so that means that we don't get anything, we don't get any subspace or subbundle of the tangent bundle. We just get the entire tangent bundle. So you could say that this is like a foliation with a single leaf, which is the whole manifold. Okay, next example. The cotangent bundle inside T plus T star. So this one, if I take 1 forms Xi and Eta, then the Courant bracket of them is just the Lie bracket of the vector parts plus these interior products and Lie derivatives, but there's no vectors around, so this is just 0. And this is independent of what twist you might be interested in. So the cotangent bundle is always a Dirac structure. It's the only a Dirac structure that we always have in any example. So it's the most boring Dirac structure if you want. And the foliation that it determines, well, if you project it down to the tangent bundle, you get 0. So it's a foliation of by points. So this corresponds to a foliation of dimension 0, whereas this corresponds to a foliation of dimension equal to the dimension of m. Okay. Okay, moving along. If we wanted a slightly different example than this, I should have remarked that, yeah, of course, we need these Dirac structures to be maximal isotropic, and this one is obviously isotropic because there's no vector part to contract. Why is this one isotropic? Well, if you try to take the norm of this element, then you're going to see that you're just plugging in this vector into this covector, but because B is a skew 2 form, B of XX is 0. And so this is isotropic as well, and it has dimension, half the dimension, and so isotropic. Okay, and the last example I'm going to give before I ask for questions is going to be a deformation of the T star. So suppose that I take T star and I try to move it by a shear in the T direction. The way I do that is by one of these two vectors, bivectors. So I'll take the graph of beta, which is beta xi plus xi for any xi inside T star. Okay, and this is I think this is a kind of surprising outcome when you check integrability. So if you want gamma beta to be involutive, with respect to h equals 0, it turns out that this is imposing the condition that the Lie bracket or Schouten bracket of beta with itself is 0. So this is maybe the first time you see it should be a little bit surprising, but it imposes a well-known integrability condition on the bivector, namely that it Schouten commutes with itself. The Schouten bracket is just an extension of the Lie bracket from vector fields to all multi-vector fields. So, if you have X wedge Y, W wedge V, right, then the Schouten bracket is defined by taking the Lie bracket of X and W, wedge Y, wedge V, plus, you have to take brackets of all possible choices of pairs. And every time that you move one of the choices by one space, you get a minus sign. So this will be X, minus, the next term will be X bracket V, but it'll have a minus sign. The next term will have a plus Y bracket V, and so on. Okay, so it's built from the Lie bracket by just distributing the Lie bracket over all of the vector fields in the multi-vector field. Okay, and so this is otherwise known as the, so this condition is equivalent to the following. So any bivector, it determines a bracket on functions on the manifold. So if I take F and G, okay, the bracket determined by beta is just the natural pairing between beta and the 2 form that you get by just wedging the derivatives of the functions together. So this is in wedge 2t, this is in wedge 2t star, and they contract together, and you get a function. So we have a bracket, and this condition is equivalent to the fact that this bracket satisfies the Jacobi identity. So beta beta equals 0 is equivalent to the condition that this bracket is Jacobi. But of course, because of the way the bracket is defined, you see how it's defined in terms of taking the derivatives of f and g. This bracket automatically satisfies the Leibniz rule in both arguments. So Leibniz is automatic. And when you add those two together, what you get is a Poisson bracket. So the point is that this graph is a Dirac structure exactly when beta is a Poisson bracket. Okay, I've given so. When Weinstein and Courant originally introduced this notion of Dirac structure, they were very struck by this interpolation. You see that one of the possible examples is that of a two-form, the graph of a two-form. Okay, and the closure under the bracket implies that the two-form is closed. So the integrability condition in that case is dB equals 0. On the other hand, the integrability condition on the graph of a bivector is that the bivector is Poisson, beta bracket beta is equal to 0. So they were very struck by the fact that Dirac structures interpolate between Poisson structures and symplectic forms, or closed two forms. Okay, and so hopefully that is clear. Any questions so far about all these examples? It's got to be some questions, yes?
I have a question, maybe going even before that, if it's fine.
Yeah, go ahead.
So I have seen this definition of Courant bracket many times, and every
Yes.
time I see it, like 1 hour later, I cannot remember the signs. I cannot remember where I should plug in X and Y. So what is the logic between this?
Why can't you remember?
I don't know. It's something wrong with me, I guess, but it's hard.
No, I think the reason you can't remember is probably because you have never you've never proved something using it. Correct me if I'm wrong, but once you prove something using it, then you'll remember it. So I don't know if you were here last time when I was explaining an ambiguity, right? So there's an ambiguity in the definition of the bracket, an ambiguity which is justified by the fact that it's a homotopy object. So you're never going to be able to remember it. You just have to pick one and remember that one, right? I mean, so the way that I remember it is that you're not gonna remember it based on logic because, like I said, there's an ambiguity. Okay, so according to logic, you should remember all of them, not just one. Okay. So that's not help. Logic is not helpful. So what you're asking is impossible. But the way that I remember it is, so to be honest, the non-skew one is more helpful for computation. First of all, so the way that I usually remember it is that, you're trying to take. You should think that x plus c is acting on y plus eta. It's like a Lie derivative, okay? So this thing is equal to the Lie derivative of x on y plus eta, minus, plus something else. There's got to be something else which involves c. Okay, and so I don't know what might be the obvious thing to write, but the thing you're supposed to write is minus IY dxc. So I guess you can remember it this way, that this is supposed to act upon the second argument, and so you should have a Lie derivative acting on it. And then this must, you need to have a derivative of xi somewhere. So dxc has got to be in there, and well, maybe you just remember that there's a minus sign here.
Okay, yeah, it makes sense. Yeah, I mean, I just thought that maybe there is higher level explanation, but as you said, there is a homotopy choice.
I can give you many high level explanations, at the end of which you will not remember for sure.
Okay.
I can guarantee you won't remember. But yeah.
Thank you.
Maybe if I may.
Yes.
Maybe a different way of thinking about it is if you think of the first argument acting on the second, as Marco was saying, but you factorize through the Lie algebra of automorphisms of t plus t star. So you think of x plus t going to x plus dg. Now dg is a two form, and now you act by the vector field and the two form on y plus eta. And there is only a natural action of acting, which is by Lie derivative on the vector field, by the vector field, and shifting by the two form.
Okay, but why should it be a minus? Why should it be a minus, not a plus?
Yeah, there is a combination that I agree. Yeah.
But it's, I mean, it's weird, right? Because it's not a convention. It's not like you can put a plus and get a Courant bracket.
No, but there is a good reason for this. This is because the map going from sections to the Lie algebra needs to be equivariant.
Yeah, okay, but you want it to preserve the Courant bracket, right? So that condition.
Well, you can define the Courant bracket as this infinitesimal action. That's another way of thinking. Anyway, it's just.
Yeah, I don't disagree, but yeah. Anyway, okay, so. Honestly, I think you should be suspicious of this thing about I can't remember the bracket and so on. I mean, I'm not picking on Yuri or anything. Okay, but do you remember the axioms for L infinity algebras? Do you remember the sign conventions for L infinity algebras? Okay, I don't. But the weird thing is that everyone complains about the Courant bracket, but they never complain about the L infinity algebra axioms. So yeah, I think there's
if it's not a cyclic sum of something equals 0, I have to look it up. I
mean, L infinity, the L infinity Jacobi identity.
I'll look it up 100
like
more.
Yeah. No, but it is like that. But there's still signs, right? Anyway, I'm just venting. So okay, so we have these examples. Okay, but now I want to point out something really important, which is that. Now that we have this graph of beta, gamma beta, and also the fact that we know that B for dB is equal to 0 defines an automorphism, this means that we can apply e to the B to this graph of beta, and this will also be Dirac structure right away. So we automatically have a way of producing an infinite number of examples. So what is that going to do? So that's going to shift this one in the vertical direction. Right, so I'm going to do e to the B gamma beta. So this is going to be what? It's going to be xi plus beta xi, but then I'm going to shear in the B direction. So I'm going to act by B on beta xi for all xi inside T star. And as long as B is closed and beta is Poisson, let's assume beta bracket beta is equal to 0 and assume dB is equal to 0, then this thing here is another Dirac structure. Okay, it's like taking a Poisson structure and moving it by a diffeomorphism. Of course, that will still be a Poisson structure. It's just that this is not a diffeomorphism; it's a B-field gauge transformation. Okay, and so you might ask, well, okay, what is this thing? And I just want to point out that that if B is small, in a sense that I'll make precise in a moment, but if it's small, then this change of beta, this change of the graph of beta, will remain a graph. Still the graph of some map from T star to T. And because it's isotropic, that means that that this beta prime is another bivector. So in other words, for small two-form B, we can deform beta to beta prime, which is another bivector, and that bivector will also be Poisson. So what we see here is a gauge transformation action, the action of the closed two forms on Poisson brackets, moving one Poisson bracket to another and producing a family of Poisson brackets. So let's just see. So if it's really true, if this really is the graph of some beta prime, then this equality should hold. And we can solve for this beta. If we solve for beta prime, we get that this is the vector part, this is the covector part, this is the vector part, sorry, and this is the covector part. We just set eta equal to that, and then we see that beta xi is equal to beta prime times eta. Eta is xi plus b beta xi. Getting rid of xi, we get that beta is equal to beta prime 1 plus b beta. And we can solve this for beta prime. We could write beta prime is equal to, well, let me do it in another step. So beta times, beta prime is equal to beta 1 plus b beta inverse. So, and actually I just want to, in order to interpret this, we have to think of the left and right hand side as maps from T star to T. So this thing inside here, this is going from T star. If we just look at this component, beta goes from T star to T because it's a bivector. B goes from T to T star because it's a two form. And so this whole thing is an endomorphism of T star. And if this endomorphism of T star is invertible, then this equation, this solution makes sense. And so to be small means that this thing is invertible. And you can amuse yourself by writing it in the following way, using the geometric expansion for this, and you'll get beta plus beta minus beta b beta plus beta b beta b beta minus etc. So we have this kind of infinite sequence of contractions. If you like indices, then this will amuse you to no end. You'll have beta ij b j k beta k l, and then you're going to have more and more of this type of contractions. So this is a kind of from the point of view of Dirac geometry, based on the small lemmas that I just explained. the fact that this is Poisson is obvious. However, from the Poisson geometry point of view, this is not obvious. It's not clear that given a Poisson bracket and a closed two form, that you can somehow manufacture another Poisson bracket, which is highly nonlinear in that two form and in the original bracket, right? You have this nonlinear transformation, which produces you another Poisson bracket, right? So this is just a demonstration of certain ways in which Dirac geometry makes facts about Poisson structures more obvious. Okay, but if this is not invertible, then what do we have? We have a new Dirac structure, a Dirac structure which is not the graph of a two form and which is not the graph of a bivector. It's something new. So this is the first example which is new, let's say, a genuine Dirac structure which is not a traditional geometric structure. Any questions about this so far?
Sorry, in the end, it is the graph of this beta prime, right?
It's the graph of beta prime as long as beta prime is indeed well defined. So as long as this endomorphism is invertible, then
Right.
beta prime is defined and it is the graph of beta prime. But if this thing is not invertible, then there is no beta prime. And so it's just a Dirac structure.
And can I just ask, I mean, I guess I don't know rigorously, but I guess I thought that up to some natural equivalence, one expects like finite dimensional space of Poisson brackets.
No, Poisson brackets have an infinite. No? They're not elliptic. Poisson brackets are not elliptic in their deformation theory. So typically there's an infinite dimensional space of them.
And so like one should expect all these beta primes to be inequivalent, like for a small arbitrary B sort of.
Yeah, yeah, that's right. Yeah, they're inequivalent. Yeah, like indeed, like for example, if you were on the two sphere, think of it as a symplectic two sphere. This would just add B to the area of the two sphere. And so if B is adding an area, then the symplectic form is even its cohomology class would be different. So it's okay. So I said, like, I was trying to I was doing a sales job. I explained how great these Dirac structures are, but in fact, the reason why this Poisson bracket is being deformed is because you can think of a Poisson bracket as a symplectic foliation, and on every leaf we have a symplectic form. And so if you take the B field and you just restrict it to the symplectic leaf, you get a two form. You could just add that two form to the existing symplectic form, and you get a new symplectic form on that leaf. And so that's really what's going on here. You're not changing the foliation, you're only changing the symplectic area, the symplectic form of each leaf.
Oh, I see.
That's what's happening here. And if the two form is too big, then you might ruin the non-degeneracy of the symplectic form. And so it might break the fact, it may break the Poisson property. It might break the symplecticity, the non-degeneracy of each leaf. That's why you need to keep the two form small in comparison to the symplectic form.
And just sorry, I think you said it, but I think it just passed me by. Like the underlying leaves of beta and beta prime are the same. You're saying you're just changing the.
It turns out that they are the same. You can kind of see that here because because if you look at this as a map, you can see that the image of beta prime is exactly the same as the image of beta, since it's, beta prime is some endomorphism post-composed with beta.
Okay.
So it's the image inside the tangent bundle will be the same.
I see.
Okay, any questions? Student questions, maybe? Don't be intimidated by the prof questions. You should ask student questions. I'm always afraid of this. Like, this happens in my seminar all the time. That the silence is inversely proportional to the seniority, which is so weird.
I wanted to ask, well, I know you said you didn't know anything about this, but I wanted to ask about the twisting.
Okay, yeah.
Can you say anything about why we twist in that way? Like, is there no way you could twist with a multi-vector instead of a?
No, the twisting. Okay, so the twisting by a three form. Okay, so the important thing is this lemma. So the lemma says that if you have a general two form, then it's not a symmetry of the bracket, but what happens is that you increase the twist. So, okay, now, so here's the key. So if you have a twist, which is by a closed three form, then what that means is that locally the three form is exact. So that means that locally the twist is by such an exact three form. Right? So you know, someone might hand you a Courant bracket which is twisted by a cohomologically non-trivial three form, closed three form. But locally speaking, the three form is exact. The twist is given by this, and therefore you can undo the twist by one of these gauge transformations. So that means that locally a Courant bracket is not twisted because you can always remove that twist. You can always gauge it away. Right? And so that's what makes it clear that the twisting is possible. That if you have the trivial twist in every open set, but then on the overlap region, you glue one to the other by doing one of these e to the b, right? Just imagine that another way of thinking of it is that in ui, you have t plus t star, but you have h equals 0. And in uj, you have the same thing, uj with h equals 0. But then on the overlap region, when you glue these together, right, you glue tui to tuj by one of these e to the b shears, right? And that will be e to the b. It will be a two form defined on the double overlaps. Okay, and the point is that in order for this to be an isomorphism, you need that the two form is closed. And in order for this thing to be a genuine gluing over three-fold open sets, threefold intersections, we need that bij plus bjk plus bki is equal to 0. So as long as you give me, because of this lemma, as long as you give me a bunch of closed two forms on the double overlaps, which allow me to glue from I to j, from j to k, from k to I, in such a way that the gluing map glues up to be a well-defined equivalence relation, then you will get something which has the local property of a Courant bracket, but which is globally defined. So it's a twisted Courant bracket. Okay, so this is just another way of representing a class in third cohomology. You express it in terms of Czech cohomology, right? So this is like if you had a three-dimensional cohomology class, you could describe it in Czech form as a collection of closed two forms on double overlaps. Instead of giving a closed three form, you could give closed two forms on double overlaps. Anyway, what I'm trying to get across is that the freedom to twist is really the same thing as identifying the automorphism group. The fact that we have local closed two forms in the symmetry group allows us to build this thing. I guess if you're confused by what I said, it's because you may be rusty on the Czech to Duram sequence. So if you look at the relationship between Czech and Duram, what you would do here for each bij defined on uij, you would multiply it by a bump function. You would extend it to a three form defined on ui, on uj, on uk, and you could convert this collection of two forms into a global closed three form. But anyway, that's really where it's from. There is no other way of twisting. And just to make a quick comment, if h is not 0, the condition on beta is that if we take beta bracket beta, this 3 vector is not 0, but rather it's a funny thing. So you take the 3 form, the twist 3 form, that's in wedge 3 T star, and then you apply beta to it, the third exterior power of beta to it. That basically raises the 3 indices of H so that they're upper indices and it becomes a trivector. This condition is what's called a twisted Poisson structure. So again, this type of structure, it's like, locally speaking, it is gauge equivalent to a usual Poisson bracket, but it's being glued together globally by these gauge transformations that we just studied here, these things. Okay. And the result is some kind of twisted Poisson bracket. These things haven't really been studied that well. It's really the case H equals 0, which is the famous one. Okay, so this is giving you a bunch of different Dirac structures. There's a bunch of other interesting Dirac structures. I'm not going to explain this one, but on any Lie group with a bi-invariant metric, there's a special Dirac structure. There exists a canonical Dirac structure which is twisted by the 3 form H. There's a natural Cartan 3 form on such a group whose value is that you take the Lie bracket of the A and B and then you use the bi-invariant metric to pair it against C. This is the so-called Cartan 3 form. And there's a natural Dirac structure, and it if we project down to T, let me call the Dirac structure L. So if we look at L and we project to T, there's a bundle map like this, and it induces a foliation of G, a natural foliation of G. What natural foliation is there of any Lie group? I think there's only one. Lie group has only one foliation by submanifolds. What is it? You see here the seniors now they should remain silent, whether by necessity or by request.
Necessity.
Sorry?
Oh, it's okay.
Anyone? Submanifolds of a group. Anyone? Thomas, I'm calling on you. You can decompose any group into special submanifolds. Why? Thomas doesn't want to answer. By conjugacy class. There's a natural action of the group on itself, and there's conjugacy classes. And this is not a foliation of constant rank. It's a singular foliation. Okay, so it turns out that this foliation actually lifts to a Dirac structure. So even though it's a singular foliation on the group, meaning that it has, like for example, the identity element is its own leaf, zero-dimensional leaf. But then if you take a generic conjugacy class, it'll have much higher dimension. And the point is that so that the tangent spaces of the conjugacy classes are all of different dimension, but it turns out that these tangent spaces are the projection of a bundle, which is this bundle L, which has constant rank. So it's a very nice fact that the conjugation singular foliation actually comes from a Dirac structure of constant rank inside T plus T star of the group. Anyway, maybe next week we'll see a kind of version of this. Okay, and so that gives a bunch of examples of Dirac structures, and now let's talk about GC structures examples.
Wait, sorry, before you move on.
Yeah.
And like you're saying that this example, the Dirac structure, is not of any of the previous types.
Yeah, it's a genuine Dirac structure, which is, yeah.
It's not like a graph or a.
Definitely not, yeah, because you can see that the projection at the identity element is 0. So it looks like T star at the identity element.
Oh, sure. Yeah.
And then at some bigger leaf, it has a bigger projection. Yeah. And so the amount that it's tilted over depends on how big the conjugacy class is. The bigger the conjugacy class, the more tilted the subbundle is. And this is the fundamental object in this whole theory of so-called quasi-Hamiltonian or group-valued moment maps. The reason that whole theory works is because of the existence of this Dirac structure. It's just that at the time that Alexeyev, Meinrenken were developing it, they did not know, they didn't think of it in those terms, but they were using all of the structure implicitly, all of the structure of these Dirac structures. Okay, so for generalized complex, remember what we need. We need a complex structure on T plus T star. Well, okay, there's an obvious way to do it. You just put a complex structure on T and then take its dual on T star. And that's going to be a complex structure. You notice that I put a minus sign on one of the two, and that's in order so that this thing is compatible with the metric, so that yeah, it's an element of the Lie algebra of T plus T star. So this is here to ensure compatibility with the metric, the inner product. So this is the complex type. Okay, and let's look at the opposite extreme, where instead of sending T to itself, imagine that T is sent completely to T star. So here we see that we see that we have a two form. We have a map which maps T to T star, and this one goes from T star to T. So in order, this has to be skew to ensure compatibility with the inner product, and this minus sign ensures that J squares to -1. And because we need this inverse here, that means this has to be non-degenerate. So this is what's called symplectic type. Okay, so this is it. I mean, this is something for if it's the first time that you see it, you need to kind of puzzle over this observation that this single type of structure can encompass complex structures and symplectic structures. So the plus I eigenspace, eigenbundle, in this case, is going to be the plus I eigenbundle of I and the minus I eigenbundle of I star. So this will be T 1, 0 plus T star 0, 1. That will be the plus I eigenbundle of J. Whereas in this case, it turns out that the plus I eigenbundle is actually the graph of I omega. So it is the set of X plus I omega X, where X is in the complexified tangent bundle. As usual, I need to complexify to get plus I eigenspaces. So this is kind of similar. So so what you see is that in both cases, you get a Dirac structure, right? Because in this case, if you try to pair this with this, because they're of opposite types, you just get 0. This is like d by dz, and this is like dz bar, so the interior product will be 0. And here, x, if I take the norm of this, then it's omega xx, and omega is skew, so this is going to be maximal isotropic. And it's also clear that we should have an I here because the plus I and the minus I should not have any intersection. So when we take the complex conjugate of this thing, it should not intersect itself. So we need some kind of imaginary aspect to this. Okay, so the last type that I want to give is some kind of mixed type, or interpolating type. Well, okay. Before that one, I could say that you could take products, c to the n cross r to the 2k. Right. This will be generalized complex. But the really interesting thing about the structure is that there's things in between. So intermediate ones they're going to be like this. So a very important class is given in the following way. So suppose that I take it to be upper triangular. A pi, wait, let me call it Q minus A star 0. So if this is the generalized complex structure, I'm not saying it's obvious that it's good to consider upper triangular, but just trust me, this is a good example to consider. So this thing has to square to -1. That means the diagonal blocks will have to square to -1. So they're complex structures. So there you see that if, and Q goes from T star to T. So Q is actually, it turns out, is in wedge 2T as a bivector. And of course, we could take Q to be 0. So if Q is equal to 0, then we just get a complex structure. But if Q is not 0, then we need to make sure that this thing squares to -1. J squares to -1 if and only if, you can, if you do the matrix multiplication, you'll see IQ minus Q I star is equal to 0. So the complex structure and the bivector must commute. So this is another way of saying that Q is of type 2,0 plus 0,2. In other words, Q kind of looks like dzi dzj plus complex conjugate. It's with coefficients and so on, but it's a sum of holomorphic plus complex conjugate, but it doesn't have any del z bar components. That's what I mean by type 2,0 plus 0,2. And then involutivity implies that it turns out to imply that that if we take IQ plus little iq, let's give that a name, sigma. So this is just arranged. I took a complex linear combination so that this, I arranged it so that this is of type 2,0, purely 2,0. So I just removed the complex conjugate part. And this is just a type 2,0 part. The involutivity says that two things. Number one, it's holomorphic with respect to I. That's a condition that makes sense for a 2-0 bivector. So it's a holomorphic section of the bivectors, and it also is holomorphically Poisson. So this means that this thing actually defines a holomorphic Poisson structure. Okay, right. And maybe the last thing that I would say is just in the same pattern that I used for Dirac structures. Remember, I introduced this this nice Dirac structure coming from a bivector, but then we could apply a B field to it. So similarly here, we could apply a B field transformation to this thing. So think of it like this: J is an endomorphism of Tm, T plus T star m, and I have some automorphism of Tm. So if I pull back J by this automorphism, what am I going to get? I'll get e to the b, j, e to the minus b. So if we compute this, this is okay. And if we work this all out, this is for the students. I'm working it all out. Then we get another example. This is, of course, it has to be a generalized complex structure. It's obtained by applying a symmetry, an automorphism of the bracket, to a pre-existing GC structure. And let's take a look at this. What you notice is that the upper right-hand corner is not affected. The lower left-hand corner is very much affected and is nonlinear in B. So this is kind of similar to what happened to the Poisson structure. Okay, and then the diagonal terms look like this. Now, so if we can arrange that I plus QB is equal to 0, so under what conditions could this happen? Well, B is the thing that we chose here. So what would B have to be? B would have to be equal to minus Q inverse I. And so therefore we can solve this exactly under the condition that Q is invertible. And when is Q invertible? It's when the holomorphic Poisson structure is holomorphic symplectic. So if we happen to have started with a holomorphic symplectic structure, and we built this GC structure, then we could apply this B field transformation, and what we would get is zeros on the diagonal. We would get Q here, and we would get, well, we'd have to work this out. So if we just inspect this thing, I can rewrite this as minus b I plus qb minus I star b. That's what this term is. And this I plus qb, assuming that b is chosen like this would imply that this term is 0. And we would end up here with just minus I star b. But if I dualize this, what I get is I star plus b star q star is equal to 0. But b and q are skew, and so they are anti-dual, anti-self-dual, and so we just get this. And so minus I star b. Sorry, what am I saying? If you work out what is I star b, so I star b and q is of type 2 0 plus 0 2, so it commutes with I. So this I star can go to the other side and you will get an I, and I squared is minus 1, so we'll get minus q to the inverse. So what you'll have here is minus q inverse. And so exactly what you find is that this is the same thing as omega inverse minus. It's a symplectic structure. Okay, so sorry, this was a long logic, so let me just recap the logic. So we started with a complex structure. We deformed it to this thing using a holomorphic symplectic structure. And then we reinterpreted this as using a B-field transform with a symplectic structure. And all this is happening inside the space, the moduli space of generalized complex structures. So within the space of generalized complex structures, it is possible to have a path from a complex structure to one of these intermediate things, which is which is obtained by using you can only do this particular change, this particular deformation, if you have a holomorphic symplectic form on your space. And so, like, for example, on a complex K3 surface or on a complex torus or on C2 or whatever, what have you. Okay, and then this thing is equivalent in the world of GC structures to a symplectic structure. And therefore, the complex and symplectic moduli spaces are unified in this way. Okay, so they're literally connected to each other. You can actually have a path going from one to the other. I think I probably have to stop, right?
Again, I mean, yeah, if this feels like a stopping point, that's fine. Or if there's a better one coming up.
Let's see. Yeah, just if I can have 10 more minutes, then it's a better stopping point.
Yeah, sure. Yeah, I mean, I think if people are here, probably they're free until 3. So, guess.
Yeah, because I've already gone over. So the people, yeah, okay, all right. So let's see. So, there was something important I wanted to say. Okay, now, okay, so in general, what can we say? So if you write a generalized complex structure in terms of its components, it's going to have an endomorphism of T, it's going to have a bivector, and it's going to have a 2 form in it. This is usually this is not a very good way of thinking about the structure. The reason is because B-field transformations jumble and kind of transform all these tensors into each other. However, there is one component which has a special role, namely the one I just erased, this one. This one is always a real Poisson structure. And so your generalized complex manifold, it will always have a singular foliation by real symplectic leaves. Okay, it will always have this type of foliation. And then you can ask what this remaining structure is. Okay, and what I would like to explain in a very simple way is that this additional structure, what it's doing for you is it's defining a complex structure transverse to the foliation. So if you zoom into the foliation and you drop you take a perpendicular to that, the idea is that this becomes complex. So near this point, it will look like a symplectic structure cross a complex structure. The complex structure is transverse to that. Okay, and there's a very highbrow, well, it's kind of highbrow, but also dead simple way of seeing why this is the case, and that is because of the following thing. So Q is a map from T star to T. It defines the Poisson structure, and it's very fashionable nowadays to think of Poisson structures in terms of this two-term complex. So we have T star and T. So the reason why it's nice to think in these terms is because T star is a Lie algebroid. It has its own bracket, and the Q is the anchor map, which maps it into the tangent bundle. So we have a Lie algebroid way of thinking of this Q. Okay, and if we think about this two-term complex as if it is the tangent bundle of the quotient, so the quotient will be the leaf space or the transversal space. So maybe I can color this one yellow. This is the potentially non-existent leaf space, the quotient of the manifold by the foliation. Okay, so this thing should have a tangent space. And what is that tangent space? Well, it's the cohomology of this two-term complex at this position, right? It's the tangent of the manifold modulo the image of Q. The image of Q is exactly the tangent of the symplectic leaves. So that means that we can represent the tangent space to the leaf space via a two-term complex on this space by taking cohomology. So the fancy way of saying this is that this is the tangent complex of the leaf space. And everyone knows that a leaf space, like whenever you try to take a quotient and it fails, then it becomes a stack. And so this is the tangent bundle of the stack. It's this two-term complex. Now this leaf space, what I'm claiming is that it should have a complex structure. It should have a complex structure. So we should have an endomorphism of the tangent bundle, which squares to -1. So what we want is an endomorphism. We want a bundle map from the tangent bundle to itself, so that when we square it, the resulting map is equal to -1. So we would want that A squares is equal to -1. But actually, when you're dealing with two-term complexes, you never write equations like this, right? Because since it's a two-term complex, you don't need for these two operations to be equal. You just need them to be chain homotopic. So in other words, you want this to be homotopic to -1, which means that you would need an additional piece of information. We need a chain homotopy going back one step. And that chain homotopy is sigma. So this equation, j squares to -1, if you write here j squares to -1, what you're going to get is what? A squared plus q sigma is equal to a squared plus q sigma is equal to -1. That's what comes from j squared equals to -1. And so if you look at this, you see that a squared minus the identity or plus the identity should be homotopic. They should be homotopic to each other. So in other words, we should have a squared plus 1 is equal to going via the homotopy and the differential plus the differential and the homotopy. But this is just a two-term complex. So we just get one term. We get sigma q. This is q. Okay, so the whole point is that underlying any generalized complex structure, there is a real Poisson structure which defines these symplectic leaves. And then the tangent space to the leaf space can be interpreted as T plus T star in a sense. It can be interpreted as, T and T star in a two-term complex, where the differential is Q. And then to have a complex structure on that means precisely that we have this j squared is equal to -1. And the really kind of remarkable thing is that courant integrability captures precisely the integrability condition on the stack, but it expresses it in terms of T plus T star. So so this is really what is going on. There's a theorem of myself with Bailey. So Bailey in his thesis had the main part of the analysis, and then we proved that near any point, a generalized complex structure is equivalent to basically to a symplectic structure cross with a complex structure where that complex structure has been deformed by a holomorphic Poisson structure. So it turns out that there's an additional structure on this transversal. It's not just complex. In general, it would be holomorphic Poisson. I think that, roughly speaking, that captures. So this theorem, to prove this fact, it turns out we needed to use the full power of this thing, which is called the Nash-Moser iteration scheme, and we needed to it's basically something that is stronger than the Newlander-Nirenberg theorem. So as a part, we needed to, there might be a better proof of this. I always intended to have a better proof of this. And by now I think we probably could obtain a better proof, but the original proof of the local normal form theorem for GC structures, it basically, it involves something that is stronger than the Newlander-Nirenberg theorem. So it was really kind of surprisingly difficult. I never intended it to be that difficult, but anyway. So yeah, so in a way, generalized complex structures are basically defining a singular symplectic foliation with a transverse holomorphic Poisson structure. I'll leave it at that for today and continue next week, I guess. If you have any questions, we can.
So this local normal form theorem you mentioned is basically saying up to diffeomorphism, like basically up to a symmetry, like diffeomorphism and B field transform, you do get a local product structure, or?
So if you want to, I mean, roughly, so to be precise, I would say that it's good, at least in your head, to distinguish between singular points and non-singular points of the foliation. So there will be an open dense set where the leaves of the foliation are equidimensional. They have a single dimension, and they're basically symplectic leaves with a transverse complex structure, and locally it's a product of those two structures. And so there's no local invariance except for the dimension of this complex transversal. That the dimension of this transversal is called the type. So if it was purely symplectic, it would be type 0. And if it was purely complex, it would be type whatever the dimension is. Okay, but there will be points, there's going to be a closed set where the dimension of the foliation is not locally constant. It's like small, it's really small. And if you move at all in any, in an open set, it will jump higher. So if you're on one of these singular points or points of smaller dimension of the symplectic leaf, then the transversal has a Poisson structure which vanishes at the origin. So it is a product structure of a symplectic structure and a complex, a flat complex space, C to the n. But that C to the n has a Poisson structure of its own, which has a 0 at the origin. And so what that is, the reason for that is obvious. The reason is that we know that when you move away from that point, the dimension of the symplectic leaf must jump higher. And so when you move away from 0 in the transverse complex direction, you're suddenly going to have a bigger symplectic leaf there, which will add to the pre-existing symplectic leaf, right? So the idea is like this. I'll just draw a picture that we have symplectic cross complex, but at the origin, there's like symplectic leaves inside this complex manifold. So there's a holomorphic Poisson with sigma of 0 equals 0. So this is a copy of C to the n. And so what happens is that if you happen to be, let me just draw the base point. So if you happen to be at this point 0, 0, right, then the symplectic leaf that you're on is this one. But if you move away from 0, 0, you might end up on this symplectic leaf cross this symplectic leaf. And so the total amount of symplectic leaf is bigger now, now that you've moved away from 0. Okay, and if you were on this point, if you were on one of these leaves, and if you use the local normal form, then it would be a product of a bigger symplectic across a complex. You know, see what I mean? Like if you happen to be at a singular location, then this factor has to contain the structure of that changing dimension. And so the way that is encoded is by a holomorphic Poisson structure. And what we also proved is that the isomorphism class of that holomorphic Poisson germ at that point is an invariant. So you cannot, so at this point, there is a local invariant, and that local invariant is a germ of a holomorphic Poisson structure. So at each point, the only local invariant, the complete local invariant, this is the theorem of Bailey and myself. At each point, the complete local invariant is a germ of holomorphic Poisson structure up to isomorphism. Isomorphism of holomorphic Poisson structures, no B fields or anything. So as you move around, the Poisson structure germ is, it is a local invariant. And for an open dense set, that holomorphic Poisson germ is 0. But there's going to be a closed set where that germ is interesting. And it turns out that the other weird thing is that closed set where the Poisson germ is non-zero, that closed set actually inherits an analytic structure, a holomorphic analytic structure, even though this whole thing is just smooth geometric structure. It turns out that degeneracy locus, it becomes what's called a complex analytic scheme. So it has a complex analytic structure. Anyway.
Thank you.
Yeah.
Others? I guess we are a bit late. So
okay, yeah, no problem.
But yeah, thanks, Marco. And so I guess next time will be more like a GK. Is that right?
Yeah, I mean, it's up to you how quickly you want me to go. If you want me to speed up and at this rate, I mean, I was expecting to do one more, but I could do 2 more with the material that I had in mind. But it's up to you. I can compress that to 1 more.
I think,
and I'm not offended. I would just, that's just
I
more
think
time for
probably
me.
2 is fine. I don't think. I mean, we've got time. I think
2 is
okay.
good.
Yeah,
okay.
yeah.
Fine.
Okay, great. Yeah, thanks, Marco.
Okay. See you later. And maybe at some point I should find out who these other students of yours are. We should.
Well, yeah. I mean, we could.
So
we could
Josh
attempt a
Jordan.
introduction.
Who's Josh Jordan? I've met him before, right? Josh Jordan. You can sign out. Anyone who can't stay, you can sign out.
Yeah,
Bye.
yeah.
Where are you, Josh?